Saxon Algebra 2, Lesson 57. If you think you came here for just an algebra lesson, I have really great news. Today you're going to get a physics lesson and an algebra lesson. I was just stopping to think, is it physics or chemistry? It might be at the place where physics and chemistry overlap. But in any case, you're going to get a sweet little science lesson, and I'm going to give that to you first. There are things called ideal gases, all right? The cool thing about ideal gases is that there are three qualities of each one. They have a pressure, they have a volume, and they have a temperature. And these three qualities or characteristics always stay in balance for each ideal gas. And if you change any one of them, the others will compensate so that the mathematical combination of these three things stays exactly the same. We have a formula that expresses that, and it looks like this. The first pressure times the second pressure divided by, the first pressure divided by, and times the first volume divided by the first temperature will equal the pressure times the volume divided by the temperature of the second set of conditions. So this will be the before and this will be the after, so to speak, right? And the problem will make it clear how we're changing things. These are the kind of problems where we're going to get 5 pieces of information and solve for the 6th. All right? So this is what you need to remember to do these problems. You need to remember that formula. And one of the things that blows students' minds about these problems sometimes is that when we're given the pressure and the volume and the temperature for these problems, they're in units that are super complicated looking. And I'm just going to show you in the book where they're written. John writes them all down for you. For pressure, look at these: newtons per square inch, atmospheres, millimeters of mercury, torts, and pounds per cubic inch. Oh, that sounds sciencey and hard. Don't worry. Volume could be liters, milliliters, or cubic centimeters. Temperature is usually kelvins, okay? Now, you don't really have to memorize these. I do want to remind you they're right here on page 245 if you need them, but usually John will word the problems so that you can figure out which is pressure, which is temperature, which is volume. It's not that hard to figure out, but here, if you're ever really confused, you can compare the units in the problem and see, well, is that a pressure or a volume or a temperature, okay? So that information is there for you if you need a little bit of sciencey help, but I think you'll be fine. Let's start the first problem and see how this works. Ready? 4 liters of an ideal gas at a temperature of 800 kelvins had a pressure of, need more light on my book, of 100 newtons per square meter. Okay, that sounded like a lot, didn't it? Let's just go bit by bit and write down, remembering that we want these 3 pieces of information. 4 liters. Okay, liters, that's pop. That sounds like volume to me. 4 liters of an ideal gas at a temperature of 800 kelvins had a pressure of 100 newtons per square meter. Okay? Now, I know for sure this one's temperature. I'm pretty sure this one's volume, and that means this one has to be pressure. And it says a pressure of. It's not that hard to figure it out, you guys. Don't sweat needing to know all those weird names. This is the first set of conditions. If the volume were increased to 10 liters, okay, so the second volume is 10 liters, and the temperature reduced to 600 kelvins, what would the pressure be? See? They tell us one set of conditions and then they give us two things that changed and ask us to find the third. It's not that hard. And later John's going to give us these same problems with crazy numbers. These are just nice and cute, so we're fine. We're going to use this to set it up. The first pressure, 100, times the first volume, 4, divided by the first temperature, 800, equals the second pressure. Oh, we don't know that, so we'll just write P2. The second volume, 10, divided by the second temperature, 600. Okay, so there's lots of ways we can do the math in this, but what I want to do before I start multiplying anything together, let's find our variable and let's just unwind whatever's over here and get all the numbers on one side and simplify in one giant spasm of canceling. All right, we'll multiply by the reciprocal to cancel these diggity dogs, right? But then we're going to have to do 600 over 10 over there, right? Because that's the one on the outside. Cancel, 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 cancel. P2's by himself. Yay! Oh, what progress. All right. Well, let's start here. 110. We can divide each of these by 10 by scratching out a 0, right? 100 divided by 10 is 10. 10 divided by 10 is 1. Okay, that's good. Let's do the 4 against the 8. That will be a 1, and this becomes 200. 200 into 600, shall we say? 1 and 3. And we get that the second pressure is, looks like we just have those two numbers, right? So it is 30. And what you can do is just go look and see what your unit was. It's pressure. So we just go back and look in here and say, it had a pressure of newtons per square meter. Okay, so we'll just write newtons per square meter. Oh yeah, I had it right there too. We don't have to understand anything about what that means to write it down as our answer. Oh, do you feel smart? Because I feel smart. And I feel smart for me and I feel smart for you. Fabulous. So that's how it works. Make sure you write that down in the cover of your book right now. Pause me. I'll just turn the page real slow. You can write it while I just turn the page slow. That was really slow, wasn't it? Right, I'm going to recopy it. I'm playing real hardball now, you guys, about making sure that you write down your equations, not only on your test problems, but on your review problems. I want to see formulas on review problems every single week, all right? I want to just beat it into you. Ouch, that sounds painful. The initial pressure of a quantity of ideal gas was 400 newtons per square meter. Okay, so that's the initial pressure. P1 equals 400. And I'm not going to write the units down this time. We don't need them. And the initial temperature was 1,200. The initial temperature was 1,200 kelvins. The volume was held constant. They don't tell us what the volume was, but they tell us that it was held constant. We can write this like so, right? Whatever the original volume was, the second volume was the same. What was the pressure if the temperature was decreased to 900 kelvins? And we want to know what the new pressure is. Okay, here is something cool. When one of the elements is held constant, when one of the variables is held constant, we can delete it from the formula. What? So in this case, V1 equals V2, we can just ignore it. We can just now use P1 over T1 equals P2 over T2. And our problem is that much easier. Again, the magic words are held constant or something like that, right? It tells us that they're the same. We can simply remove them from the formula. Oh, it's just that much easier. So let's fill it in. 400 over 1200 equals something over 900. Now, if you're into proportions, you can see really fast how this is going to work out. 400 into 12, we can see that's 1 over 3, just like that, right? Divide each by 400, and then we can see, oh, if this is the same 1 and 3 ratio, then P2 has to be 300, right? I could cross multiply and, you know, do all kinds of cute things to solve that, but it's that easy. I can just see the pattern in the numbers. And again, I want to put a formula on it. This is newtons per square meter again. It just so happened that in both of these problems, we solved for pressure. In this one, we were able to eliminate volume because it was held constant. In the first one, we had all three. Okay, we just have one more. I think I can make it fit. The temperature of a quantity of ideal gas was held constant in an experiment. Aha! So T is held constant. Hallelujah, happy days. That means we can use P1V1 equals P2T2, right? Fabulous. Let's get some data here. Oh, wait. That's a V. Sorry. I'm glad I caught that because you're probably sitting there going, wait, what? No, I just wrote the wrong letter. T and V, they rhyme. Okay. Where am I? The original pressure was 7 atmospheres. Oh, it's a different unit, but again, John has never done anything so fiendish as to switch units in the middle of the problem, so we don't have to worry about that. Just check and make sure that it sounds the same. But he has never, to my knowledge, done anything so heinous as to mix the units. The original pressure was 7 atmospheres and the original volume was 42 liters. If the volume was reduced to 10 liters, what is the final pressure? All three of these are solving for pressure. That's just coincidence. All right. 7 times 42, right? P1 is 7. V1 is, excuse me, 42 equals P2 times 10. Let's divide both sides by 10. I'm going to leave this 10 here because scientists love decimals. As mathematicians, we're cool with fractions. We really like fractions. But scientists they dig the decimals. So I can see, oh, this is actually going to set me up nicely for a decimal answer. So I'm going to leave it like this and write my answer as a decimal. So I'm going to multiply 42 times 7. 14, 28, 29. Whoops. What is happening with me today? It's 294 over 10. So it's going to be 29.4 equals P2. And the unit is atmospheres. Not only math professors, but science professors love it when you put a unit on your calculation. So I'm going to be a real stickler for that. I want you to get in the habit of always, whenever there are words in the problem, put a word in your answer, right? You don't have to write a novel, but just stick a word in there. All right? Oh, I hope you feel smart. Look at how smart looking those problems are. They sound very complicated and difficult, don't they? But when you crack the code and learn how to use that formula, they're kind of nifty. All right, I'm done talking. I hope I haven't done too much damage to your day. That is lesson 57. I will see you soon for lesson 58. Goodbye.